In our previous lecture, we introduced the Riemannian metric, Riemannian manifold, and gave some examples. And then we showed that there is a special connection on the Riemannian manifold. It's called the Levi-Civita connection or the Riemannian connection. And this connection is compatible with metric, and the torsion is free. Today we will mention about the Christoffel symbols. First, let's say if Mg be a Riemannian manifold, and the vector field, let's say xyz, vector field on this manifold, and then we have this identity 2 times g nabla xyz equals xgyz plus ygxz minus z gxy. So then we have some bracket expression. So bracket xyz plus z xy and minus yz x. So we have this identity. This one is called the causal identity. And you remember when we proved there is a special connection, Levi-Civita connection. From Riemann manifold, we arrived this identity, or the contrary converse case. If you have this one, you can construct this connection. So now we will define the Christoffel symbols. So Christoffel symbols. So what we are going to do is this. Let's say you have, let delta xi be a frame. So it means at the point tangent space, this is a for, let's say, for n, this is a base. So of course if the dimension of the manifold m, so this will be goes from 1 to m. So then we define this one, delta xy delta xj equals from k from 1 to n. So gamma ijk delta xk. So this gamma ijk is called the Christoffel symbols, and these are the differentiable functions. So you see, if you have these Christoffel symbols, you can define the connection, and you can calculate this connection by using these Christoffel symbols. So remember, when we mentioned about the Riemannian manifold, we told this metric actually determines all the information you need from the manifold. So now the question is it possible to find these Christoffel symbols in terms of these metric components? So now we will show this is possible and find the exact formula for the Christoffel symbols. So first, consider this one in the Christoffel is in the causal identity x delta xi, and let's say y delta xj, and z delta x k. So we put this information here. So it means you have 2 times g. Also, let me remind this agreement. We put this xi, xj as g sub ij. So I will use this symbol to denote this expression. So the first one, we have this one, x I, x j, x k. So let me put t here because I use the k there. Let's put this one r. So I will change this one also. This is r. So the right side becomes g jr xi plus g ir xj minus g ij xr. So now we write the bracket expressions. So first bracket xy, so it means x I xj xr plus, now we have zx, so it means you have xi and xj, and then plus minus g, so you have xi, xj, xr and xi. So let me check the last one. Yeah, yzx. Okay. But for f differentiable functions, we know that this one x xi x xj f will be f xi xj minus f xj xi. So you see this because f differentiable, it means is continuous, so it will be 0. So we have this only this part. Also we can write here this one as gamma ijk. So we have this one 2 times ijk g rk equals to this one, this part. Okay, remember this part, this is the components of the matrix of the metric tensor. So if I want to find this gamma, so I will multiply this one by inverse matrix components. So in that case, only these terms g rk will be 1, the other all terms will be 0. So it means you have this one ijk equals 1/2. So now I put this rk and then this remaining part. So this is the formula for the Christoffel symbol, and you see if you have G, the metric, you can find the gamma, and using this to find the nabla, or you can continue this one. So if you have metric, then it will be enough to calculate the Christoffel symbols, and then find the coordinate derivative. Okay, now let's calculate for one example how to calculate these Christoffel symbols. So our example is this. So consider this Riemannian manifold G. G is not canonical metric here, it's given in these terms. So 1 plus x square dx square plus dy square plus e to z dz square. So find 1, 1, 1 and 1, 1, 2 for Riemannian manifold and G. So our M is R3. Okay, first let me bring this formula. So we have this formula. Okay, let me put here. Okay, now we will find the 1, 1, 1. So first let me put this number here. So you have 1R, because the components, the metric is symmetric. I can write in this form, no problem. So here we have 1R xi. So remember x1 will be x, x2 will be y, x3 will be z. So the remaining part 1R over x, so 1 minus 1, 1 xr. So this one is 1, not I. Okay, now we take the summation for R. So for the 1, we have this one. And you see you have 1, 1, 1, 1 minus 1, 1. So you have G11 x1 plus 1 half G12. So then you have this one. Two minus plus. Okay, so again you have 2 times 1, 3, 4 x1 minus 1, 1 x3. Actually, if you look at this one, we need to find the matrix component. So let me put these components here. So first we have this one. So you have 1 plus x squared, 0 and 0, 0, 1, 0, and 0, 0, e to z. Okay. So then the inverse matrix will be 1 over determinant G, and then adjoint matrix of G. So by using this formula, we can find these inverse matrix components, and will be 1 plus x squared, 0, 0, 0, 1, 0, Okay, then 0, 0, e to negative z. So here we have this one, 1, 1, 1, 2, 1, 3, and also we have this one, G2, 1, 1, G2, 1, 2, and G2, 1, 3. So if you consider this one into this comma 1, 1, 1, so first one, 1 over 2, G2, 1, 1, so 1 plus x squared. So this one, because we have 1 plus x squared, it means 1 plus x squared, and according to which variable? X, because x1, x. Then, if you look at the G2, 1, 2, 0, G2, 1, 3, 0, so you have 0, 0. And then 1, 1, 1 will be 1 half 1 plus x squared 2 times x. So you have this 1, 1, 1 x over 1 plus x squared. So this is the first part. So the other part, 1, 1, 2. Okay, again, let me bring this one here, this one. So now I am calculating this one. 1, 1, 2. Okay, 1 half. So you have 2, 1. So now first let me look at this one. Okay, this one G2, 2, 1, G2, 2, 2, and G2, 2, 3. So if you look at G2, 2, 1, it is 0. So that's why I don't need to write this one, because this will be 0. Plus 1 half G2, 2. If you look at G2, 2, it is 1. So I put here 1 and write the inside. So because R is 2 now, it means 1, 2, x1, 1, 2, x1 minus 1, 1, x2 plus, again, if you look at the G2, 3, we are here now, so then you have 0. So our remaining part is 1 half, so we have this one, x1 minus x2. Okay, if you look at this one, G12, so G12, you see 0. So this one is 0 minus G11, x2. G11, 1 plus x squared. So 1 plus x squared. But we take the derivative according to y variable. So it's 0. So you have 0 here. So this one, 1, 1, 2 will be 0. You see, by using this formula, we can calculate Christoffel symbols, we find for this manifold we find the two components, but you can find the other components in a similar way. So it will take some calculations, but the method will be same. Okay, that's all for this